All right, thanks for joining me. Thanks for listening. If you're reading closed captions across the bottom of this page, then you're probably not getting everything you need to. I would encourage you to get some headphones, make sure that you're listening to this. We're moving on to the second part of our second unit, which is projectile motion. So it's a little bit similar to the vector things we've been doing, but the math is going to be a lot different. So we're going to go through some concepts. I'm going to work one example math problem, and then we're going to call it a day. And then we'll pick up next time just working out some more math problems and hopefully getting good at doing that. So you got a handout to work along with this. Again, oftentimes my handouts don't just have you copy, so you kind of need to look at both. So what we're going to be doing is describing and calculating the motion of an object that's thrown or kicked, basically something that's flying through the air. So first unit was things going straight, and again, now we got things going through the air. So a few vocabulary words: projectile, trajectory, parabola. Those are on your note sheet. So I'm just going to kind of hit these real quick. And again, I'm going to move through the video quickly. You've got the ability to pause and stop. So if you need to write things down, you write things down. This is the way I can get through the video pretty quickly, and you do what you need to do. So a few vocabulary words. A projectile is something that is projected or thrown. It's basically something that's launched by force moving through space. A ball flying through the air, an arrow flying through the air, a rocket, anything that is kind of like in the image that you see there. So, and if it's a projectile, it's got two things going on. It's going side to side, but it's also going up and down at the same time. So we say it's got motion in two dimensions. If we're looking at a coordinate system, it's got motion in the X and Y direction. Trajectory, it's a big fancy word, but it's just the kind of the path that it takes when you set something on a trajectory. Usually that has to do with the angle that it's leaving at, and that causes the shape of something kind of flying through the air, as long as nothing is pushing it anymore, which is a parabola. And you can see the picture here. A parabola would be the curved path that we have there. So I'm asking you to take a moment and put these three words together in a sentence, just kind of show that your meaning and what you understand with the meaning with it. So again, you might want to pause for the second to do that. One of the things about projectile motion is understanding items moving in both the X and Y direction. So we're looking at things in two dimensions, X and Y. So again, X is going to be our side to side dimension. If you're thinking about a coordinate system in geometry, X's are going side to side, and then Y is going to be going up and down. One of the key things about a projectile is that the X and Y motions don't influence each other. In other words, they're independent of one another. The image that's on your screen, the ball that's moving through the air, the red ball, its side-to-side motion, which is the arrow pointing to the right, has nothing to do with the up and down motion. And if you look at what's going on with the ball, these arrows are vectors, and they're specifically velocity vectors. And so what they're doing is they're giving us an indication of how fast the ball is moving in two dimensions. If we simply look at the X dimension to begin with, which is the side-to-side, hopefully you'll notice that as the ball moves through the air, the length and the direction of this arrow stays exactly the same. However, the Y arrow, which is the one that's going up and down, as it's going up, you'll notice that the Y arrow shrinks until it disappears, and then it starts growing again as it goes down. Now, this Y arrow is real similar to what we talked about in the first unit. As we send something, if we throw something up, it's going to slow down until it hits it's what's called an apogee, or the top of its path. At that point, it stops for a moment in terms of its up and down, and then it's going to return back to Earth, and it's going to speed up because gravity is pushing it. So this is a really key image, and I'm asking you to label another image on your note sheet very similar to this to see if you can kind of apply it to another situation. But again, you'll notice what happens is basically, if there's no air, the speed of the projectile, or the ball in this case, doesn't change at all as it moves from left to right, but the speed changes as it goes up and down because gravity. So once it leaves our hand, or once it leaves our whatever we're pushing it with, the only force acting on it at that point is gravity. So the only thing accelerating it is gravity. The only thing that's going to be happening is it's going to change its speed up and down. It will not change its speed side to side if there was no air. Again, on Earth, we do have air, so it will slow down slightly, but in general, it's not going to slow down left to right. On our formula sheet, we're going to be using the projectile formulas over here. They look a little bit crazy, but they're really just the same formulas on the left-hand side but they've got X's to them, which means we use those formulas if we're doing something to side, and some of them have Y's on them, which means we're doing those if we're talking about something moving up and down. So you'll notice there's a D formula for the X, and that's velocity times time. And then there's a D for the up and down, which is basically the same formulas that we have over here. Again, you'll notice D equals VXT is really just the same formula as this one, it's just rearranged. The second formula under projectiles is really the same thing as this fourth formula over here. One slight difference is it uses the letter G instead of the letter A, because in this case, G stands for gravity. I'm going to ask you to write that down in a moment, but the letter G, it replaces A because it is the acceleration due to gravity, which we've used before, and it's 9.8 meters per second down, oftentimes written as negative 9.8. So we'll be using some of the formulas over here, although they are really just repeats of the formulas over here, specifically for moving left or right and up and down. So one of the questions I've got for you on your handout over here on number 4, and again, if you haven't filled out everything for number 4, you probably want to pause your video and look at what you've done so far. My question says the time it takes an object to hit the ground will change depending on how fast it's being thrown or shot horizontally. This is kind of a true-false statement. So in other words, if I've got an arrow, if I've got a ball, no matter what it is that I've got, if I throw it as hard as I can on a straight line, does that change how long it stays in the air? And most of us think that it will. However, I've got this little video. Hopefully this pops up correctly so that you can see it. Sometimes I've tried this before and it doesn't seem to work all that well. But hopefully if you're seeing this guy's got a contraption where he is able to drop and project a ball at the same time. And what you'll notice is, hopefully you'll see that they end up hitting the ground at the same time. So the ball that's dropped straight down, which is that one. And then there's a ball that's being projected. So this will be a projectile that's shot. Again, if you watch them, they end up hitting the ground at the, there we go. Come on, dude. Let's get it going. You'll notice they end up hitting the ground at the same time with that. So the answer to the question is false. Projecting the ball left to right has no effect on how long it hits. And that's a huge thing in this unit. I'll say that one more time. The speed with which we throw something left to right, or we throw it off of a cliff, it doesn't matter if it's the speed of sound, it's going to hit the ground at the same time as something that would just be dropped. There's no difference. There is an exception to that, which I was saying that unless something's moving really fast, like the moon, because the Earth's surface does curve. So if something was moving super, super, super fast, it actually wouldn't hit the ground at the same time because our Earth is curved and things could go around the corner there. But most times we're not doing that. So the side-to-side motion has no effect on how fast the object falls. You need to kind of remember that one. So this picture that we've got here, it doesn't matter if you throw it just with a little bit of speed or you throw it with a lot of speed. After the same amount of time, the ball is going to be have fallen the same amount. Now, again, if it's going super fast and does the Earth's curve, then we got a different issue there. So the only effect is pushing harder makes it go farther before it hits the ground. That's it. It doesn't make it stay in the air longer. It just makes it go farther because it's going faster and it's covering more distance before it hits. Still hits the ground same amount of time. Huge key fact. We'll see test questions over that. Okay, so as far as velocity goes, horizontal velocity, side-to-side velocity, mentioned this earlier, it's going to stay the same. So we throw a ball, it's going to, once it leaves your hand, nothing else is pushing it side to side. Its speed should stay the same, again, if there's no air. And we use the formula distance equals velocity times time. Up and down, however, there's gravity. And so the speed of an object is going to slow down as it goes up, and it's going to speed up as it goes down. And we can do the math like we did in the first unit to talk about how long it takes for something to fall. Okay, so neglecting air resistant motion is constant in the side-to-side direction. However, motion will change in the Y direction. On your handout on page number 7, I'm asking you to do a little task with this image. So you probably want to pause your video and attend to that for a moment so that you can get that done. Once you've got that done, we're going to move on to doing some math problems here. All right. And so we're kind of skipping down to another page. So I'm going to work out one problem with you today, give you an example of what we're going to be doing. So hopefully you can just kind of copy this down. There's a whole lot of information on your sheet about what we need to do. But basically, we've got two sets of motion. So we're going to end up having basically two sets of equations that we have to work on. So I'll give you an example in a moment. Basically, we're throwing something off of a cliff and trying to find out some information about either how long it's in the air, or how far it goes, or how long it takes to hit the ground. So sometimes we have enough information to solve our X equations. Sometimes we have enough information to solve Y. So we need to write all of that down in order to figure out what we need to do. No Pythagorean theorems here. Generally, finding out the time it takes is going to be our first step, and it's usually the most important variable for us to figure out. Right? And we're going to try to make sure that we list our X motion side to side and our Y motion up and down separately when we're writing our things out. We're largely going to be using the formulas in this part of our reference sheet, and we'll work on those here in just a moment. Again, D with the little X, that's our range. In other words, how far does it go left and right? Whereas D to the Y is how far is it going up and down? This is generally our height. So they're both D's for displacement, but they're in different directions. X is side to side, Y is up and down. So when we're doing these, I would encourage you, the first thing to do is draw a diagram. Remember to keep your X's and Y's separate from each other. Remember that something falling has an acceleration of -10 or -9.8 meters per second. We often use -10 just to make the math easier. So let's do one. All right, so here's example one. We got a stone thrown horizontally at 7.5 meters per second from a cliff that's 68.4 meters high. How far away from where we threw it does it end up landing? All right, so step one was hopefully just kind of sketch this out so that you have a picture of it. And then what we need to do is think about what do we need to solve. And I'm taking a little moment here. Our first step is almost always to figure out the amount of time it takes to hit the ground. So keep that in mind. That's kind of usually the first place to go with this. If we look at our problem and we write down the things that we know, you'll see up here, again, a stone is thrown horizontally at 7.5 meters per second, right? And then it's from a cliff that's 68.4 meters. So in terms of distances, we don't know the distance left to right, which is actually what we're trying to solve for. We do know the distance up and down, which is 68.4 meters. And since it's going to be going down, we can call that negative. In terms of a velocity, we know the side-to-side velocity is 7.5 meters per second. It's falling, so we know what the acceleration is up and down, which is going to be -10. We don't know the time that it's going to take to hit the ground. And I want to, again, note here, the time that it takes to hit the ground is the same time in both of them. So this is why I'm saying usually we have to solve for time, because if I know the time in one, then I can know the time in the other one. All right. We also know that the rock is not moving to start with, so its initial velocity in the up and down direction is 0. So these are all the things that we know. Again, the green is what we're trying to solve for. We can figure out the green if I know V and T over here, but again, I don't know T. So think of it as a puzzle. How do I figure out T? Well, if I come to the Y side, I've got enough information over here on the right to figure out the time. Once I figure out the time over here, it's the same time over here. And then I can multiply these two together to get my answer. So we'll go through it step by step. All right. So again, I've got things in the X, but I got two unknowns in the X. I can't use them. What do I have in the Y? I've got a bunch of stuff, and I've got enough stuff to use this formula because I've got a distance. I've got an initial velocity. I don't have a time. I do know gravity, and I don't know time. Just like we did in the first unit, the initial velocity is going to be 0. And so I'm going to work this out just kind of step by step. Again, you should probably be copying this and working it out on your own, pausing each time you need to, just to make sure you know what's going on. So here's our formula. We got it from over here. It's the fourth, excuse me. Where'd it go? There it is. So we got the second formula. Plugging in my numbers, my distance was -68. My initial velocity was 0. I don't know time. G is acceleration of gravity, which is -10. And again, I don't know time. So I substitute all my numbers in and think about what happens. 0 times time, this is going to go away. And what I'm left with is 1/2 of -10. So I'm going to distribute or multiply 1/2 of -10, and that's going to give me -5. right, so that's going to make this whole section right here negative 5t. So if I simplify this, I get negative 68.4 equals negative 5t squared. So again, pause when you need to so you can write things down and keep up. We're trying to get t by itself. So I need to get the negative 5 off. Since negative 5 is being multiplied, I got to do the opposite, which is to divide. So I'm going to divide both sides by negative 5. Once I divide the left by negative 5, I get 13.8. And that's going to leave me with t squared. And we've been doing this several times this year. We're not done yet because we're solving for t squared. We're solving for t. And so I need to take the square root of both sides. If I take the square root of 13.8, my time ends up being 3.7. Okay, great. We got an answer. We're done. No, we're not. All right, because t is our time, which is 3.7. That's not what we're trying to find out. We're trying to find how far does the stone land. But we needed to get this first, so then we can come back over and now plug it in to the x part, because we're trying to find the distance that it goes. We knew how fast it was going, but we didn't know how long it was flying. Now we know how fast it's going. We know how long it's flying, so we should be able to figure out how far it goes. So we can change now to the x formula. Like I said, this is usually a two-step problem. And my distance is simply velocity times time. So I'm going to do 7.5 times 3.7. That's going to give me my answer of 27.8. Okay. So hopefully you've been able to write all that down and kind of see one example with this. My next video is I'm going to go through a couple more examples with you, just so we can kind of go through the process of it and then hopefully be able to work some of the things out on your own. So we're not going to start working out example 2 yet. Again, hopefully you got everything worked out on your sheet. If you need to go back and rewatch parts of the video to get everything done, please do so. And please ask for help if any of this did not make sense.